December 7, 1941, Pearl Harbor burns, and Lieutenant Colonel Hugh Casey studies his Pacific campaign maps in frozen disbelief. Every crimson marker shows where America urgently requires air bases, coral reefs, jungle flats, hostile coasts. His figures are merciless. 40,000 tons of concrete, 300 men, 45 days minimum for one runway. At that rate, the conflict would conclude long before half the needed landing strips even existed. 6 months later, the Bataan Peninsula. U.S. engineers abandon their half-finished runway as enemy troops approach. 6 weeks of brutal labor, 200 tons of concrete, gone because time ran out. Meanwhile, in a Pittsburgh steel plant, metallurgist Gerald Greulich sketches an unthinkable idea during lunch: steel plates punctured with holes. His co-workers burst out laughing. "Jerry, planes land on solid ground, not on cheese graters." Army officials agreed. "Mr. Greulich, you expect us to land a 15-ton bomber on perforated steel. This is flight safety, not bridge work." What they didn't see was that Greulich's outrageous vision would soon let American pilots touch down anywhere on Earth within a day, not in spite of the holes, but because of them. The mathematics behind one engineer's improbable design was about to reshape modern warfare forever. December 7th, 1941. The attack on Pearl Harbor had ended 6 hours earlier. Yet Lieutenant Colonel Hugh J. Casey remained motionless inside his Honolulu office, gazing at the Pacific operations map spread across his metal desk. Smoke from the shattered harbor drifted in through open windows, thick with the bitter scent of fuel and scorched metal. Red pins dotted the chart like an infection. Wake Island, Midway, Guadalcanal. Countless coral atolls and forested clearings where the U.S. must build airfields if it hoped to strike back across 6,000 miles of ocean. Casey lifted his slide rule and began computing. Each runway demanded 40,000 tons of sand, stone, and cement, 300 trained workers, and 45 days of clear weather. He traced his pencil down the list of islands, multiplying the totals. The arithmetic was merciless. With current manpower, the Army Corps could complete barely a dozen major strips each year. Yet more than 60 key sites across the Pacific would decide victory or defeat. His aide, Major Robert Stevens, entered carrying new intelligence files. "Sir, the Navy projects will need operational runways at 37 forward points within 18 months to support Admiral Nimitz's counter-offensive." Stevens placed the folder and studied the figures. "How many can we actually finish by then?" Casey tapped his pencil against the map. 18, 20 if the convoys hold and the Japanese leave us alone. The meaning hung in the air like smoke from the harbor. America could lose the Pacific not from battle, but from concrete. By February 1942, Casey's nightmare was real. The Bataan withdrawal had turned into chaos of abandoned airfield works. Engineers blew up their own half-built strip to prevent capture. 6 weeks of exhaustion. 200 tons of material ferried 8,000 miles from California, obliterated by U.S. explosives. The enemy's advance simply outran American construction. Reports echoed the same story. At Wake Island, Marines poured only foundations before assault forces struck. The runway existed merely on paper when the garrison fell. At Clark Field in the Philippines, an enormous concrete extension stood 70% complete, useless without its final month of finishing. The pattern was relentless. Concrete demanded stability, steady supply chains, secured ground, continuous work, conditions no battlefield could promise. Peacetime airport methods proved disastrously unfit for a war fought across islands that changed hands weekly. Casey began to doubt every lesson from West Point. He had been taught runways must be permanent, immovable, built to serve for decades. But what worth had permanence when battles shifted in days? Why build eternity for a base that might be lost in weeks? Before the final evacuation from Manila, Casey wrote in his logbook, "Concrete runways are luxuries of peace. The perfect has become the enemy of the good, and the good the enemy of the possible." The line would prove prophetic. He had no alternative yet. 8,000 miles away in Pittsburgh, Carnegie steel metallurgist Gerald G. Greulich flipped through Aviation Week over lunch. Its February issue lamented airfield delays strangling America's advance operations. Greulich examined the grim photographs of abandoned concrete pours and unfinished airstrips, then reached for his ever-present notebook and began to draw. His engineer's instinct instantly recognized the core flaw. Concrete runways were single, rigid systems, either perfect or useless. There was no in-between, no means to assemble or repair them rapidly under battlefield pressure. But what if airfields could be built like bridges? What if prefabricated parts could be forged in US factories, shipped anywhere, and joined together like massive steel puzzle tiles? Greulich's pencil swept across the page, forming rectangles lined with circular holes. His co-workers at the next table noticed the sketching and leaned over curiously. "Jerry, what are you scribbling this time?" "Another truss beam," joked Tom Morrison, a structural engineer who had partnered with Greulich on several Pennsylvania rail projects. Greulich looked up calmly. "Runways, built from perforated steel panels that interlock." He showed the drawing, rows of 10 by 2 foot plates patterned with evenly spaced holes. Morrison burst into laughter so hard he nearly spilled his coffee. "Jerry, planes land on solid ground, not on Swiss cheese. You can't drop a 15-ton bomber onto metal full of holes." The rest of the cafeteria erupted with laughter, but Greulich continued penciling numbers, undisturbed. Later that afternoon, alone inside Carnegie Steel's metallurgy lab, Greulich began working through the load distribution math that would soon revolutionize warfare. His slide rule clicked steadily as he charted stress behavior over perforated surfaces. Conventional belief said holes weakened metal. His equations proved the opposite. When calculated properly, perforations increased strength, dispersing tension instead of concentrating it, an idea every bridge designer understood, but no one had dared apply to airfields. By nightfall, Greulich had filled 12 pages of data confirming that his perforated planking could support aircraft up to 20 tons, while consuming 60% less steel than solid sheets. Each panel would weigh 66 pounds, light enough for 2 men to lift, yet durable enough to absorb endless bomber landings. The math was undeniable, even though it overturned decades of accepted aviation doctrine. He closed his notebook and stared through the lab's frosted windows at the orange Pittsburgh skyline, lit by Carnegie Steel's furnaces. Somewhere across the Pacific, American pilots were dying for lack of landing grounds. The answer sat in his calculations, waiting someone brave enough to trust mathematics over habit. March 15, 1942. Gerald Greulich stood before a chalkboard in Carnegie Steel's main conference room, facing 12 senior engineers and 3 Army procurement officers who had driven in from Washington. On the table before them lay his prototype, one 10 by 2 foot panel weighing exactly 66 pounds, punctured with 384 precision-cut holes arranged in a geometrically perfect pattern. "Gentlemen," he began, chalk scraping rhythmically against the board, "stress distribution through perforated steel behaves like that in an I-beam. The voids don't weaken the plate. They redirect force across the entire surface." He drew arrows, showing how impact loads spread through the perforations, turning point pressure into distributed strength. Each section sustains 75 pounds per square inch repeatedly, providing nearly a 3-to-1 safety margin for a 15-ton bomber. Major William Harrison, the lead Army procurement officer, eyed the display with doubt. He had spent 20 years supervising concrete airfield projects across the continental United States, and Greulich's proposal contradicted every safety principle he believed sacred. "Mr. Greulich," Harrison began carefully, "I admire Carnegie Steel's creativity, but we're discussing aircraft operations, not bridge architecture. Pilots require smooth, solid runways. This looks like factory flooring." Greulich had expected this reaction. He had rehearsed for weeks, knowing military officials distrusted anything unproven. "Major Harrison, may I demonstrate?" Without waiting for consent, he stepped onto the steel panel and began to jump up and down. The metal flexed slightly but held firm. "I weigh 170 pounds, he said evenly. "This piece bears my full weight across 2 square feet, roughly the same pressure exerted by a B-25's landing wheel." Harrison remained unmoved. "Mr. Greulich, a B-25 weighs 15 tons and lands at 90 miles per hour. Your footwork hardly counts as a flight test." His voice carried the unshakable confidence of a man who had watched countless runways crumble under the strain of warplanes. Career. Moreover, perforated plating, they argued, would trap debris, cause waterlogging, and reduce tire traction during wet weather operations. Greulich had prepared thoroughly for these objections. He turned to a new sheet in his engineering notebook, revealing precise computations on friction coefficients and drainage flow. "Actually, Major," he began evenly, "the openings improve drainage by letting water pass through the surface instead of collecting on top. And regarding traction, steel surfaces, when treated properly, outperform concrete in grip, particularly during rain." The Army officers exchanged doubtful looks. Captain Douglas Wheeler, Major Harrison's technical assistant, voiced what everyone else was thinking. "Mr. Greulich, even assuming your figures are right, this is aviation under combat conditions. A single structural failure could destroy a bomber and kill its entire crew. Why gamble with unproven material when concrete has been safe for 20 years? Greulich sensed the meeting slipping through his fingers. Military procurement culture valued caution over innovation. Yet he knew, from Lieutenant Colonel Casey's Pacific dispatches circulating through Washington, that traditional runway methods were failing disastrously in the field. "Captain Wheeler," he asked carefully, "how long does it take your teams to build a standard concrete strip?" Wheeler flipped through his folder. "Minimum of 45 days, under perfect conditions and no interruptions." He hesitated, realizing the trap. "Of course, those conditions rarely exist in wartime." "Exactly," Greulich replied. "These perforated steel panels can be produced in U.S. factories, shipped globally, and turned into working runways within hours, not months. No cement, no curing, no heavy equipment. 2 soldiers can carry a panel, and the interlocks assemble using nothing more than hand tools." Harrison folded his arms, unimpressed. "Mr. Greulich, quick assembly is meaningless if the strip collapses during its first mission. Our pilots deserve certainty, not experiments that might kill them." He gathered his documents, clearly signaling the meeting's end. "I'll include your proposal in our technical review, but the Corps of Engineers will want extensive trials before authorizing such a drastic change." The discussion ended with polite nods and vague assurances. Greulich stood by the window, watching the Army sedan disappear down the road, already knowing his innovation might die buried in bureaucracy. Traditional procurement moved at peacetime speed, and war demanded the opposite. 2 weeks later, his breakthrough came unexpectedly. Captain John Thompson, recently reassigned from the 805th Engineer Aviation Battalion to Wright-Patterson Field, was sorting through construction proposals when Greulich's technical file reached his desk. Unlike the earlier visitors from Washington, Thompson was uniquely suited to judge it. He had flown P-40 Warhawks during the Philippines campaign, landing on makeshift fields most engineers would have condemned outright. The stress data caught his eye, but what struck him more was how directly the idea addressed the problems he'd lived through. He had touched down on coral beaches, jungle mud, and cratered strips that barely qualified as runways. Thompson examined every page with growing respect. The precision was remarkable, and the practicality undeniable. On April 2nd, he drove to Pittsburgh for a personal inspection. For 6 straight hours inside Carnegie Steel's test hangar, he and Greulich evaluated prototypes, running through every operational detail. How easily can a damaged section be swapped out? Could it still work with a panel missing? Will the joints hold after dozens of takeoffs? To each, Greulich answered with solid data and measured confidence. Then Thompson lifted a 50-pound concrete block and slammed it repeatedly against the prototype deck, mimicking aircraft landing shocks. The steel flexed, absorbed the energy, and returned to shape without the slightest crack or bend. "Mr. Greulich," Thompson said quietly, running his palm along the ridged, perforated surface. "I've landed on worse and lived. This feels stronger than half the emergency runways we fought from in the Pacific, Philippines." Thompson's endorsement carried an authority that no procurement skepticism could dismiss. He combined first-hand combat flying, engineering knowledge, and command over active airfield projects in the European front. When he forwarded his technical review to the War Department, urging immediate field testing of Greulich's perforated steel runway design, it gave military aviation leaders the credible validation they had lacked. By May 15th, authorization arrived to construct a prototype at Wright-Patterson Field. Greulich's equations were about to face the ultimate judgment, the weight of real aircraft. Success would redefine combat engineering. Failure would confirm the dominance of concrete once and for all. June 23, 1942, Wright-Patterson Field, Ohio. Captain John Thompson stood beside a 30,000-foot airstrip, unlike anything listed in military manuals. 1,500 perforated steel panels spread across the open grassland, each piece fastened to the next through Greulich's interlocking hook system. From a distance, the field shimmered like a massive metallic chessboard, its thousands of precision-drilled holes glinting under the morning sun. Thompson checked his wristwatch. 8:30 hours. In half an hour, test pilot Lieutenant Robert Mitchell would make aviation history, the first official landing on a perforated steel runway. The stakes were enormous. Colonel James Devine, chief runway engineer for the Army Corps, had flown in from Washington to evaluate whether Greulich's system could truly replace concrete in the war zones. Devine's resume read like a history of American airfields, from Kelly Field in Texas to Hickam Field in Hawaii, each one poured in concrete, reinforced with steel, and built over long months. The idea of landing heavy bombers on a patchwork of metal sheets felt heretical. "No matter what Greulich's numbers suggested, Captain Thompson," Devine said, studying the glittering surface through binoculars, "I've witnessed experimental surfaces fail spectacularly in tests. If this setup collapses under a 3,000-pound trainer, imagine the results with 15-ton bombers under fire." His tone wasn't dismissive. It was protective. Too many pilots had died from runway collapses for him to take chances with untested technology. Thompson understood, but his experience gave him a harsher standard of safe. "Colonel," he replied, "I've landed crippled fighters on stretches of ground that would make peacetime inspectors faint. The question isn't if this meets peacetime rules. It's whether it works better than concrete runways will never finish under combat pressure." He pointed toward the assembled field. 12 men built this in 8 hours. To pour a concrete strip this length would need 300 workers and 6 weeks. At exactly 0900 hours, Lieutenant Mitchell's AT-6 Texan trainer approached final descent. The single-engine aircraft, 3,000 pounds fully loaded, was the smallest operational model in the Army's fleet. If the planking failed here, it would never reach the bombers. Mitchell leveled off and touched down at 65 miles per hour. Thompson braced himself for disaster. Instead of a crack, a ringing metallic tone echoed, a resonant hum of steel flexing and springing back. The plane rolled smoothly, braking to a stop 800 feet later. "Feels as solid as concrete," Mitchell reported through his headset. "No vibration, no slippage. Surface looks odd through the cockpit, but handling's perfectly normal." He taxied to the far end, throttled up, and launched again along the same metallic strip. The runway held without a ripple. No seams lifted, no buckling under thrust. Devine, however, remained guarded. "Captain, an AT-6 is no proof of combat readiness. We're talking about B-25s and P-47s, machines that weigh 5 times as much. I can't endorse this until we see those trials." His caution was justified. Procurement choices determined the fate of entire squadrons, and one premature approval could cost countless lives. Thompson nodded, prepared. "Understood, Colonel. The next 2 weeks are scheduled for progressive load tests. Tomorrow we bring in the B-25 Mitchell, 15 tons, 90 miles per hour, landing speed. If successful, Thompson intended to advance toward fully loaded transports and finally the heaviest bombers in active service. His schedule followed disciplined engineering logic, not reckless experimentation. The B-25 trial commenced on June 25th under clear Ohio skies. Mitchell's bomber descended toward the perforated field at normal operational speed, twin Wright R-2600 Cyclones throttling back into landing mode. Through binoculars, Thompson observed the 15-ton aircraft strike the steel matting with far greater impact than the earlier trainer test. The panels flexed noticeably beneath the load, distributing stress through the interlocked grid precisely as Greulich's equations had predicted. Runway response excellent, Mitchell reported after rollout and taxi. Adequate traction, no surface shift, normal handling across all ground phases. His measured report carried immense influence. Military evaluators trusted pilot testimony above all engineering theory. Colonel Devine's skepticism began to erode as data accumulated. His professional instincts admitted that Greulich's analysis was technically valid, even if it overturned decades of accepted construction practice. At the same time, dispatches from the Pacific Theater underscored a worsening emergency. Airfields lost, timelines failing, concrete useless under fire. Lieutenant Colonel Casey's messages pleading for faster runway systems reached top command, fueling demand for innovation despite institutional resistance. By July 15th, Wright-Patterson trials had proven the perforated steel planking reliable for aircraft up to 20 tons. Pilots across multiple aircraft classes, from single-engine fighters to medium bombers, reported consistent performance. The interlocking plates showed no fatigue after repeated takeoffs and landings, and installation speed dwarfed concrete's sluggish timelines. The turning point arrived when Devine submitted his formal report to the War Department. Perforated steel planking meets design expectations and exhibits acceptable operational integrity for aircraft use. Recommend immediate acquisition for combat field. Evaluation. The man who had once dismissed the system now endorsed it on empirical grounds. Carnegie Steel received an urgent order for 50,000 panels by August 1st, with production targets of 2,000 units daily at full capacity. Each sheet demanded 384 precision-drilled holes, galvanizing against tropical corrosion and strict inspection, since one flawed section could compromise an entire airstrip. Greulich personally oversaw the ramp-up, working 18-hour shifts to maintain the precision his calculations required. Scaling from prototype to mass manufacture revealed new challenges: rivet tolerances, coating adhesion, and assembly alignment. But by September, the Pittsburgh works were producing at wartime speed. The impossible idea, once doodled on a lunch napkin, had become the backbone of U.S. air power projection. October 8, 1942. Casablanca, French Morocco. Captain John Thompson stood knee-deep in Atlantic surf as Liberty ships offloaded the first combat shipment of perforated planking onto the North African coast. Operation Torch had begun 72 hours earlier, and American forces urgently required airfields to support the inland advance against Vichy French positions. Concrete construction would take 6 weeks. Time General Patton's armor could not spare, while German reinforcements poured in from Tunisia. Thompson's engineer battalion had rehearsed PSP assembly for 2 months at Fort Belvoir, but battlefield reality bore little resemblance to testing ranges. German Stukas strafed the beaches, and French artillery bracketed the landing zones. Each 10-by-2-foot panel weighed 66 pounds dry, 10 more when soaked with salt spray and sand, and exhausted troops dragged them ashore through pounding surf. The interlocking hooks, flawless in Ohio trials, now clogged with grit and corrosion, demanding constant cleaning before alignment. "Sir, we've got 800 panels ashore and ready to lay," shouted Sergeant William Morrison, pointing towards stacks of gleaming steel half buried in wet. Sent toward orderly stacks of perforated steel neatly arrayed in geometric grids along the Casablanca shoreline. Engineering projections call for 15. 100 panels to complete a 3,000-foot strip capable of supporting P-40 Warhawk missions. Morrison read from his field manual, double-checking PSP specifications against aircraft weight charts. At current offloading speed, we'll have enough sections by 1800 hours, he added. Thompson glanced over his tactical situation map. A German reconnaissance planes had been circling since sunrise, and intelligence warned that Luftwaffe bombers based near Rabat were arming for strikes against the beachhead. Air cover would be essential within 24 hours. Sergeant Morrison, begin PSP assembly immediately with what we have. Extend the field as more panels arrive, but I need 1,500 feet ready by dawn. The process revealed both the brilliance and the shortcomings of the system under fire. Greulich's interlocking layout allowed lightning-fast construction. 2 men could position and secure a section in under 3 minutes using only hand tools. Yet North Africa's terrain brought new complications. Fine sand infiltrated the joints, demanding constant cleaning to prevent separation, while the desert heat expanded the steel enough to loosen connections unless spacing was maintained to exact tolerances. By 1800 hours, despite repeated Stuka raids that halted progress several times, Thompson's battalion had completed 2,000 feet of runway. The gleaming metallic expanse looked alien amid Morocco's dunes, a silver grid laid across the ochre landscape. Curious local villagers gathered nearby, astonished to see an airfield materializing where only sand had existed hours before. At 06:30 the next morning, Major Robert Johnson approached the strip in his Republic P-47 Thunderbolt. The 7-ton fighter, loaded to maximum fuel and ammunition capacity, represented the system's most demanding test yet. Thompson raised his binoculars, knowing this landing would decide whether PSP could truly serve in combat or remain an experimental curiosity. Johnson's Thunderbolt descended at 85 miles per hour and struck the perforated surface with its trademark weight. The steel flexed, resonating with the metallic hum Thompson had come to recognize from Ohio trials. Yet the panels held firm, no separation, no fracture. The fighter rolled smoothly and came to a controlled stop in under 800 feet. Runway surface acceptable for combat use, Johnson reported over the radio. Handling normal. No vibration or irregularities. By October 10th, the Casablanca PSP airfield was fully operational, launching 12 P-47 sorties against German positions near Rabat, every successful takeoff and landing validated Greulich's mathematical models of load distribution and proved that speed of assembly outweighed all doubts. More importantly, the runway had given General Patton's advancing columns immediate air support, something 6 weeks of concrete work could never have achieved. Within 48 hours, word reached General Henry Hap Arnold, commander of the U.S. Army Air Forces. His vision of global air dominance depended entirely on rapid airfield deployment across every front. PSP had just turned that vision into reality. Arnold ordered production to expand massively, 500,000 panels to support Mediterranean and Pacific operations. Carnegie Steel's Pittsburgh mills switched to continuous round-the-clock output, with 3,000 workers dedicated solely to PSP fabrication. Quality control tightened as volume soared, but Greulich's blueprints proved forgiving enough to maintain strength despite minor variances. The final proof came on December 15th, when Admiral Chester Nimitz's Pacific Fleet began using PSP to extend Henderson Field at Guadalcanal during Operation Cartwheel. The new planking doubled the base's operational length in 72 hours. No cement, no curing, no vulnerable construction delay for enemy artillery to exploit. By year's end, 47 PSP airfields were functioning across 3 war fronts, from Morocco's coastlines to the South Pacific Islands, each one a living monument to an engineer's improbable idea. Once dismissed as lunacy, now the very foundation of Allied air superiority, exceeded 150 miles of perforated steel runways. sustaining operations from single-engine fighters to four-engine heavy bombers. The mathematical precision that Greulich had once sketched on Carnegie steel napkins was now proving itself under the harshest realities of war. Yet the ultimate test still loomed ahead. Intelligence from the Pacific reported that Japanese artillery units were adapting new targeting tactics specifically aimed at U.S. airfield construction. Fixed concrete strips, immovable and exposed, had become perfect bullseyes, crippled for weeks after every bombardment. PSP's modular system promised rapid repairs in theory, but those claims had never been proven under direct enemy fire. The Anzio beachhead would provide that crucible, where failure meant not academic embarrassment, but the collapse of an entire Allied front. January 22nd, 1944. Anzio, Italy. Captain John Thompson crouched inside a water-filled crater 50 yards from the PSP runway that served as the lifeline for 36,000 Allied troops pinned on the narrow coastal plain. German 88mm shells had pounded the area for 18 straight hours in an effort to destroy the perforated strip that allowed American P-47 Thunderbolts to support the trapped divisions. At those 3:15 hours, one direct hit obliterated a 200-foot section of runway, leaving a jagged crater conventional engineering would have called impossible to repair in combat. Through field glasses, Thompson studied the damage while fresh explosions rumbled across the perimeter. 27 PSP panels lay twisted and broken, their interlocks torn apart by the concussion wave that gouged a pit 15 feet deep and 30 across. Standard repair doctrine called for bulldozers, concrete fillers, and 48 hours of curing, resources nowhere near available on a besieged beachhead, where German observers on the surrounding hills could see every Allied movement. "Sir, we've got P-47s inbound at 0600 for support of the British 1st Division," Sergeant Morrison shouted over the thunder of shellfire. "Without them, General Lucas says our lines won't hold till nightfall." His assessment captured the brutal equation of the beachhead. Without aircraft, the ground position would collapse. Thompson had drilled his engineers for precisely this nightmare during Fort Belvoir training. Yet nothing in the manuals compared to working beneath live artillery and rocket salvos, while Messerschmitt's strafed supply trucks hauling replacement panels. The genius of Greulich's modular concept would now meet its moment of truth. "Sergeant Morrison," Thompson ordered, glancing at his watch, "form 12-man teams and stage replacement sections at the crater edge. The Germans have line of sight from Monte Battaglia. We'll move only between their firing intervals." It was a strategy forged from hard experience, work in rhythm with the enemy's gun cycle, not against it. German barrages came roughly every 12 minutes, granting fleeting windows of silence. At 0400 hours, the first team sprinted across the open field, lugging panels toward the smoking crater. They had time to fit and lock perhaps 4 pieces before the next barrage forced them back to cover. Under that rhythm, PSP's real brilliance emerged. Each 66-pound panel could be lifted by 2 soldiers, hauled over wreckage, and latched into place with standard wrenches. Damaged sheets were replaced singly, without disturbing adjoining sections, a feat no concrete runway could achieve. Even as shrapnel hissed overhead, the crews worked with mechanical precision. One squad pried out the mangled remains. Another slid fresh panels into alignment, hammering the hooks into engagement. Sparks and dust filled the air as the silver lattice grew inch by inch. The strange steel surface that had seemed experimental in North Africa now felt indispensable in Italy's mud and smoke. By 0530 hours, the men had secured 18 new panels, shrinking the gaping void from 200 feet to barely 60. Thompson quickly calculated that Thunderbolt pilots could safely clear that remaining gap during takeoff and landing cycles. Full restoration would come later, but for now, the PSP runway and the survival of the entire beachhead were once again within reach. Runway restoration demanded 9 additional panels to regain full capacity for heavier aircraft, such as B-25 Mitchell bombers. The critical turning point came at 05:45 hours, when German spotters discovered the repair activity and shifted their artillery directly onto the PSP airstrip. Thompson could only watch as 88mm shells detonated across the half-repaired runway, hurling molten metal and shattered debris in every direction. Any traditional concrete surface would have been obliterated by such concentrated bombardment, requiring weeks of reconstruction with heavy machinery, equipment the Anzio beachhead simply did not possess. Instead, Greulich's modular system absorbed the punishment with astonishing endurance. Panels that suffered direct impacts were mangled beyond use, but surrounding sections held firm. The interlocking pattern distributed each shockwave across adjacent units, preventing the chain reaction failures that plagued rigid runways. Even better, damaged plates could be detached on the spot and swapped with spares pre-staged around the airfield. At exactly 0600 hours, Lieutenant Robert Johnson's P-47 Thunderbolt appeared through the morning haze, descending despite the continuing barrage. Johnson knew the runway repairs were incomplete, but his mission, close support for Allied troops under heavy counterattack, could not wait. Thompson steadied his binoculars as the 7-ton fighter touched down on the patched PSP strip at regulation landing speed. "Surface stable," Johnson reported after braking to a stop. "Panel joints firm, no vibration through rollout." Within 15 minutes, he had refueled, rearmed, and roared back into the air, using the same repaired section, proving PSP could sustain non-stop combat operations under live enemy fire. The Anzio trial confirmed PSP as essential to Allied air superiority. By February 1st, Thompson's engineers had rebuilt the airstrip, 7 separate times following heavy shelling, each. Restoration completed in under 4 hours, using replacement panels ferried in by LSTs. The cumulative destruction that would have rendered a concrete runway useless barely slowed the modular steel surface, which could be repaired indefinitely so long as replacement panels were available. Detailed field reports from Thompson's unit reached General Mark Clark's 5th Army headquarters, emphasizing PSP's extraordinary resilience and speed of repair. Clark's analysis concluded that perforated steel planking had permanently transformed coordination between air and ground forces by removing the fatal vulnerability of static airfields to artillery. News of the Anzio performance spread rapidly through Allied command. Within days, General Dwight D. Eisenhower, Supreme Commander of Operation Overlord, was reviewing PSP schematics himself. The forthcoming Normandy invasion demanded immediate tactical air support, which meant functional airstrips within 24 hours of the first landings, not weeks later, as concrete would require. The elegant equations Gerald Greulich had once penciled on a Pittsburgh cafeteria napkin were now shaping global strategy. His unorthodox insistence on perforations had done more than solve an engineering problem. It had altered the tempo of warfare itself. One civilian metallurgist's refusal to accept old assumptions had forged a tool that bound air power and ground operations into a single, unstoppable instrument of victory.